All right, I'm going to go through and do the questions on the OneNote under the practice questions one page. I'll try and do this fairly quickly. Okay. Uh, this says a small rubber band, a small rubber stopper of mass 0.05 kilograms is whirled in a horizontal circle at a constant speed using a string. The tension in the string provides the centripetal force required to keep the stopper moving in a circle. The relationship between the radius of the circle R and the centripetal force F is investigated. And this is represented with this formula here. F for force equals m for mass multiplied by v squared for the velocity squared divided by the radius. The stopper was rotated at a constant speed of v equals 1 meter per second. So what was changed in this experiment was the radius. So the radius was changed and the force was measured 3 times using 3 trials. Cool. We can see a plot of the force on the y-axis and the radius on the x-axis. And the first question is asking us to calculate the mean force acting on the stopper for each radius. Okay, well, I'm just going to do one radius and I'll just show you what calculating the mean force might look like as a solution. So I'll draw in here. Let's go for a blue. Oops. All right. You can just write mean if you wanted. The mathematical way of doing it is x bar equals the sum of x values over the number of values. Okay, so the sum of the x values are going to be each of the trial values, so I'm going to do the mean for 0.1. Okay, so 0.508, 0.495 and 0.502. So it's going to be equal to 0.508. Oh, drawing line. Okay, got it. 508. 0.495. 0.495 plus last value here is 0.502. Divide that by n, the number of values. Well, there's 1, 2, 3 values. Sorry for the bad line there. I will calculate that now. You're welcome to skip ahead as you wish. 0.508 plus 0.495 plus 0.502 divided by 3. Oops. Times 3 is 0.502. I'm going to round that up. Cool. So good practice for you to go through and do that for each of these. The next question says, determine the absolute uncertainty in the mean force for each radius. All right, well, I will just do the first radius again. So this table has it set out as range and absolute uncertainty. What I could do is just quickly show you the formula, physics. So one of the first formulas we have here is the absolute uncertainty. I will copy that in, paste that here. Okay, so it says the absolute uncertainty of the mean, which is what we're trying to find here, so this is in your formula book, equals the max value minus the min value divided by 2. And you know the max minus min, well, that is the range. Okay, so I need to determine the maximum value at that data point. So for radius is 0.1, my max value is 0.508, and my min is 0.495. Okay, so I'm going to write that in. You can just write uncertainty is equal to 0.508 minus 0.495 divided by 2. And that is going to be 0.508 minus 0.495 divided by 2. 0.0065. Alright, so quite a small value there. Again, go and do that for each of the values. I'd suggest doing it by hand. Okay, now we are moving on to a linearized graph where what is being plotted here, I do now realize there should be a title associated with these graphs. I'm sorry. Figure 1, the mean force on a rubber stopper moving at a constant speed, and the radius is changed. And we'll go down here. We are now looking at figure 2. Figure 2. This is the mean force on a rubber stopper speed against radius. Variations of that would be fine. Okay, so we have now been given a linear plot, and we have equations that we are given. The first question asks us to identify the physical meaning of the gradient in the context of this experiment. What the hell does that mean? Okay, well, what you need to do first is look at what is, let me just, in figure 2, what is being plotted. So if our y value is equal to the force and our x value is equal to 1 over r, we can go up to the equation that we were given in the question, right? You'll be given any of this sort of information in the data set or the question. And we can look at the formatting of this. So we're given the formula force F equals mv squared over r. We could rewrite that as force equals mv squared multiplied by 1 over r. And now we are seeing our y value and our x value, okay, as is given here. X is 1 over r, and our y is f. So that means what we are left with here is our gradient. Since this is a linear plot or a linear trend line represented by the equation of the line we're given here, y equals mx plus c. So therefore the gradient of the linear trend line mass times velocity or speed squared. That is the physical meaning. The gradient is a value which is the mass multiplied by the velocity squared. Okay? So if you are asked to identify the physical meaning of a gradient, you are really just being asked to identify what does it stand for in a formula, or like what is it represented by in the formula that's given. Okay, so in this case, mass times velocity squared. Okay, the next question says identify the mathematical relationship between force and 1 over r, including gradient uncertainty and y-intercept uncertainty. All right, so we have looked at questions where you've been asked to identify the relationship, and generally you might not be given an equation of the line. The key word here is the mathematical relationship, which we are given, because the mathematical relationship, as I've identified up here, between force and 1 over r is given by this equation. Okay, so from the graph, or figure 2, just to be clear, figure 2, y equals, let's get that equation, 0.0503x minus 0.0011. Okay, so I could go and turn this into the equation where I sub in, for my x value, I might sub in 1 over r, because it's literally the x is 1 over r. And for my y value, I might sub in the force. So I can rewrite this as force is equal to 0.0503 times x. And we've identified up here, x is 1 over r. Let's say times 1 over r minus 0.0011. Okay, so that's the mathematical relationship between force and 1 over r. Easy. The next thing we need to do, which has a few more steps to it, is we need to identify or determine the gradient uncertainty and the y-intercept uncertainty. Okay, so what you'll notice here is I am underlining key things that are required from me in this question. I would recommend you do the same in an exam setting. It really helps you to communicate, not to anyone but yourself, what is required. Okay, so what is the gradient uncertainty? What is the y-intercept uncertainty? Well, in our linearized graph, force against 1 over r, we are given two other equations. We are given a maximum equation, which is this orange line because it's quite steep. The gradient is at a maximum. And we are given a minimum, which is this green line where the slope is less, and this can be seen where it's 0.04. Okay, so you could consider this as being our range, or providing us with our range values. Looking back up here at, where is it? This equation. When we are finding the absolute uncertainty, it is our max minus our min over 2. In this case, we are given a max and we are given a min, and we are asked to find the uncertainty. That's all we need to do. So we can say that the gradient uncertainty is equal to the max gradient minus the min divided by 2. We are just taking the absolute uncertainty. And we can do the same for the y-intercept. Equals the max minus min divided by 2. All right, let's do the gradient uncertainty first. So the max value is 0.0604. And the minimum value is 0.0401. And we're dividing that by 2. What's that? 0.0203. Zero point 0.015. Cool. And we can now do the same for the y-intercept. So the max y-intercept is negative 0.0763, and the minimum is 0.0753. Okay, so quite large in comparison to the equation of the line. All right, so the maximum is the negative value. So we do want to bring this negative value in. Negative 0.0763 minus our positive value is 0.0753. Divided by 2. Okay. And 0.0763 plus 0.0753 divided by 2 equals 0.0758 minus. Okay, so now we need to pretty well just take those values and include them into our mathematical relationship. So we have our equation, and in that equation we're given our gradient value. We need to include our uncertainty of that gradient value. You've got to think about it. What we are doing here is making sure that the uncertainty values from our trials are making their way all the way through to the end, and we are not losing uncertainty throughout the process. Okay, so I will do this in a slightly different color. Let's go for green. Now we can write in our equation. Force is equal to, I'm going to do a brackets here, 0.0503 plus or minus 0.01. I'm just going to leave that there due to the 0.0102. Let's just go to that. Times 1 over r minus 0.0011 plus or minus 0.0758. Okay, so you'll notice that I've left the minus off here because it just becomes plus or minus so it's transferred over. All right. Use your gradient to determine the experimental value for velocity. Calculate the percentage error if the theoretical value is 1 meter per second. All right, let's see how we go. I'm mindful of the time. I don't want you to have to watch too much of this. So we know from up here that our gradient value is the mass multiplied by the velocity squared. We have a number for that. So our gradient value equals 0.0503, and we know that our gradient equals mass times velocity squared. We are trying to determine this value for velocity, not velocity squared, just velocity. Okay, so we want to rearrange our equation to just get velocity by itself, because we have the mass. The mass is given to us in the question. If you have a look up the very top, the rubber stopper with a mass of 0.05 kilograms. So I might even write that in down here. The mass is equal to 0.05 kilograms. So I can rearrange. What I will do, I'll do my working here in color pink. All right, I'm going to divide both sides of my equation by m to get rid of the mass and isolate the velocity squared. And now I'm just going to flip it, so I have v squared is equal to 0.0503 divided by m. And I need a little bit more space here. And to get the velocity by itself, then I will take the square root of both sides. Take the square root of both sides. This will cancel out this square here. And the velocity is going to be equal to the square root of 0.0503 divided by m, which is 0.05 kilograms. Cool. And I will calculate that. Divided by 0.05 square root of that. Our answer is 1.002, well, I'll round that up, 1.003 meters per second, which is extremely close to, if not an accepted value for 1 meter per second. I'm not going to worry about the percentage error, just because I'm mindful of the time that this is taking. So we'll just cross that out. You can have a go at doing that. The formula is on the formula sheet. It's going to be extremely small because 1.003 is very, very, very close to 1. All right, last two questions we have. Use your graph to identify the force acting on the stopper when the radius is 0.22 meters. Okay. Well, when the radius is 0.22 meters, we are asked to identify the force acting on the stopper. So what we can do is go to our linearized graph and literally find out what the force is based on the trend line. So our linearized graph, we have 1 over r. So what I will do first is at r is equal to 0.22 meters, 1 over r is going to be equal to 1 divided by 0.22. And that should be around 0.55. 0.22 equals 4.54 recurring. So what we need to do now is to go up to our graph and draw on it and try and identify where this is going to happen. Can I draw a line? No, I'm going to just have to do this very poorly. I will do it in rainbow. So 0.5454 recurring. So I'm going to say if that's 4, that's 6, then this here must be about, that's going to be 5. Geez, that is very bright. Let me just change this to a different color. Just go to purple. I'll get quite a thin line. So that's 5. So then halfway between these two must be about 4.54, let's say. So with your ruler, you will draw a nice line up. I'm going to try, oh, nope. I'm not skilled enough to, oh, maybe I could just insert a line. Nope. Yes, let's go for a line from here. Up to around there. Perfect. And now I will draw a line from there across to the x-axis, to the y-axis. Let's try that again. Oh, that is not a line. Alright. So where this line intersects the x-axis, intersects the trend line, sorry, we can draw that across. And now we have our point. So if we're saying that's 0.2, this is 0.3, that's 0.25, or maybe around here is 0.25. Let's say this is around 0.225, 0.23. Obviously, this is some estimation. There is error involved, but I'm going to say that that is around, force is roughly equal to 0.23 newtons. Cool. So that's some interpolating on the graph. Last one, predict the force required when the radius equals 0.4. Now, you can actually just have a look at the formula that the graph gives us. It literally gives us an equation to determine the force. So we are going to ignore the uncertainties. So, force equals 0.0503 multiplied by 1 over r. So force equals 0.0503 multiplied by 1 over r minus 0.0011. We can sub r equals 0.4 meters and literally just do the calculation. 0.053 times 1 over 0.4 minus 0.0011. and my answer is 0.1245 newtons. Cool. All right. I hope you didn't just watch this whole thing. Go through and just find the moments that you need to. And what I will say is just practice these sorts of questions on the other revision sheets. There are there are a variety of skills that are required across these four, but by practicing these, you will be more prepared. All right, thank you.